Now let's look at this example. So this example is very important example because we are going to see few things that we have talked about but we have not really seen in the examples, which is that the chase test is the actual test that you should use to check whether the decomposition is lossless or not, because successive chaining or successive joining the tables might not give you the correct result. Okay, so let's do this using our first method that we have seen, which is the successive joining or successive combining the decomposed relation. So we have method 1. So here you have a relation, original relation, which is A, B, C, D, E, and you have these functional dependencies. And the decomposition has been done into 5 different tables. So we have AB, we have AC, we have BC, we have BE, and we also have ADE. Okay, now let's try to combine these tables and let's try to ensure that we can combine them into one using the successive chaining method, which is basically we'll check whether the common attribute is a key of one of them. If it is, it means that they can be combined safely without any lossless without any lossy information or any loss in the information. So we have AC over here. Okay, so what is a common attribute over here and here? So we have A, common attribute. Now can A determine B and can A determine C? So we have to check that. For that, what we'll do is we'll find closures of all these attributes. So we'll find closure of common attribute, which is A. So the closure of A is A can determine A only, right? It can't determine anything else. So A can't determine B and A can't determine C, right? So these two cannot be combined together. No problem. We might be able to combine it with some other table. So let's try to combine it with some other table. Let's try to combine it with the table BC. Okay, so what is a common attribute here? So the common attribute is B. So we will try to find if B can be a key to any of these two relations. So we have B plus. So what can B determine? So B can determine D. B can obviously determine B. And B can determine D. Can B determine anything else? Can D determine anything? D can determine E. Can D and E determine anything? A and E can determine, B can determine, C can determine, D can determine. We have covered all of them. So the closure of these two attributes is, or this attribute B plus is BDE, right? So B is not a primary key or a super key to either of these relations. So B cannot determine A and B also cannot determine C, right? So we can't combine these two tables. So this combination is also not possible. What about, let me try to combine this with this particular table, which is there. So let me try to combine this. Here again the common attribute is B and we'll try to see if B can be combined with one of these tables. So B can be combined with one of these tables. We'll combine them. So B here, B can determine E, right? So B can determine D and D can determine E. So we can combine this table. So we'll combine them. So we'll have A, B, E and we'll have AC, BC and ADE. Fine. Now let's try to combine these two tables, AC and BC. So AC and BC have a common attribute, which is C. So we'll take C closure. We'll try to find what all can we derive from C. So C can derive C, C can derive D also, and D can derive E using this dependency. Can we derive anything else from here? So here we have AD, which we don't have. Here we have AE, which we don't have. B also we don't have. We had C, we had D, we have covered all of them, right? So these two tables I cannot combine. AC and BC cannot be combined together, right? No problem. We'll try to combine these two tables maybe. Okay. So can I combine these two tables? So let's see. Can I combine AC with this? So we know that AB cannot be combined with AC. We saw this here, right? Though the E attribute has been added over here, it's not common. The common attribute is still A. So we can't combine these two as well. Fine. So now AC cannot be combined with this. AC cannot be combined with this. If AC can be combined with this, we might be able to solve our issue. So here we'll try to combine this with ADE. So what is a common attribute? So common attribute for both is A, right? And what is A plus? So A can determine only A, right? So we can't combine this AC with any of these three relations, right? So AC cannot be combined with any of this. So even if I combine this and this, it cannot be combined with any of these relations, right? So what does it mean? It means that you will not be able to combine these all these into a one relation, which will give you a lossless relation or a lossless composition, right? So hence we can conclude that this is a lossy decomposition from the successive chaining method. If you are still not convinced, let's try to combine these two and maybe do the full completion. Let's try to combine these two. So can I combine these two? So there is no common attribute between these two, so I can't combine this, right? Now what about BC and ABE? So ABE and BC also have common attribute, which is B. And we already saw that B can determine BDE, right? So it can't be key to either of these relations. This also you can't combine. Can you combine AC with ADE? So A determines A only, and it doesn't determine anything else, right? So you can't combine these two also. So all of this cannot be combined. So now you can't combine any of these tables, and when you can't combine any of this, you might conclude that this is lossless. So conclusion here is lossless. But is this really lossless? Okay, so we'll see that. So I told you that we should always be using chase method or chase test whenever we are testing the decompositions which are not of the binary form. Here the decomposition has happened into 5 different tables, right? So it's not a binary decomposition. So here we should always use chase test. So let's try to do this. Also here we'll see one thing about chase test, that the derivations are not exactly possible always. So how do we substitute extra variables there? So pay close attention to this. Okay, so we'll create the initial chase test table. So how many attributes do we have? We have A, we have B, we have C, we have D, and we have E. Okay, and how many tables we have? We have 5 tables. So we'll create 5 different rows, each corresponding to one of the tables. So we'll have 5 rows. So this is row 2, this is row 3, this is row 4, this is row 5. Okay, here you have this is there. Now you have AB, AC, BC, BE and ADE. Fine. Now we'll fill the initial values. So here we'll fill A and B because we have AB attributes over here. Now we'll fill A, C over here. We'll fill B and C over here. We'll fill B and E over here. We'll fill A, D and E over here. Okay. Now one by one we want to use the functional dependencies and fill this table, right? So I'll write down the functional dependencies that we have. So we have AD determines B, we have AE determines D, we have B determines D, we have C determines D, and we have D determines E. Fine. Okay, now let's start with the first functional dependency, which is AD determines B. So wherever the value of A and D are same, we have to fill the same value for B. So here you can see that here we have same value for A, but D it's blank, right? So it could be any value, I don't know. It could be different value also. So for sure I cannot say that these two rows have same value for A and D combination. So I really can't do anything about it right now. So I'll go to the second dependency, which is AE determines D. So let's look at the AE determines D. So this is the same case here as well. Though these two rows have same value for E, they don't have any value for E, right? Until I'm not sure whether this value is same for E or not, I can't do anything about this. So I'll just move to the next FT. So I'll go to the next FT, which is B determines D. So now here you have B determines D, right? So here there is single attribute. Now all the values for B is same. So we should have same value on D, right? But I can't determine what exact value it has to be, because it can be D, maybe, I don't know, but it can be some other value. But whatever value it is, it has to be the same value. Okay. So what I'll do is I'll place a variable over here, and I will place the same variable to reflect that this value that I'm putting over here should be the same value. Whenever you are able to find at least one of the value of x, you have to replace this with you have to replace x's all over the place. Okay. So here I did not know what this value is going to be. I'm just putting a dummy variable here, which is x. Okay. Fine. So given this, we have done this. Now let's go to the fourth dependency, which is C determines D. So here these two have same value for C, so they should also have same value for X, right? So what is the value? Same value for D. Now D has value X, so we'll fill the same value X over here. Okay. Now we'll see D determines E. So how will we fill D determines E? So we'll look at column D. Now here we have the same value for D, which is X, right? So this should have the same value for E over here, right? So looking at this dependency, I can see that whenever the value of X, the value of E should be E, right? Small e. It means that all over these places, the value of E should be small e. Fine? Okay. Fine. So I have completed one pass over the functional dependencies. I have filled in some tables. So I will go again and try to find if I can fill the table more. So I will come back here, which is this. AD determines B. So now A and D should determine B. So here you can see that the combination of A and D is AX and AX over here, right? So they should have the same value for B. So this row has the value of B, which is small b. So this row should also have the same value for B, which is small b. Okay. So we have covered this. Now we have to go to the other FD, which is AE determines D. So here you have same value for AE in 3 tuples. So they should have same value for D. But here we have placed a variable x, right? But now we can determine the value of x based on this row. So here you have AE. AE determines D. Okay, so the value here is AE D, right? So if any row has value AE, it should always be D, right? So this variable we can now replace all of these two variables and with only these two variables, right? Because here only in these two rows we have the same combination A and E, right? So here we can replace it with D. Obviously the x value also have the same value, so we'll replace all of them. So we have D over here. Fine. And if you observe very closely, you will see that we have a complete row over here, right? So complete row over here, it means that this is a lossless decomposition. But what we saw in the successive joining, that it was saying that it's a lossy decomposition, right? Because we were not able to combine the tables completely into one table using the common attributes. So we thought in successive joining and successive combining of these tables, this was lossy. But chase test actually gave us the right result, which is this is the lossless decomposition. So I want to first of all emphasis on this fact that on non-binary decompositions, binary decompositions always use the chase test. Fine. Other thing I want to tell you that if we are using successive joining, if you are using successive joining method, if it says lossless, then definitely it's going to be lossless. Then correct answer. This is going to be correct, right? But if it says lossy, then we have to use chase test. Then you should actually, it can actually be correct or incorrect. We have to check. So why go through this method, right? Why do you even want to go through this? Always use chase method or chase test. Fine. So it could be correct or not. This can be determined. All of these things can be determined by chase test. So chase test will always give right answer. Okay, so I'll suggest you practice chase test a lot, and basically you should use it rather than using successive joining, because that can result in a incorrect answer.